Hi, this is Parametric Equations Day 1, and so what we're going to do today is we're going to be sketching curves. We're going to be changing from parametric equations to rectangular equations and back. So the process that we're going to kind of use for sketching the plane curve is we're going to create an orientation table. We're going to plot the points of the XY values in order of increasing value of time in the table. We're going to connect the points, and then we're going to draw arrows on the graph to show the orientation from the table. Orientation, or the direction of increasing t-values, must be shown on the graph to be a parametric graph, because the addition of the parameter is the addition of time, so you have to show the movement on the graph. So if you don't have arrows on your graph, it is not a parametric graph. Then when it comes to the point in the lesson where we're changing forms, we're changing from rectangular equations to parametric or vice versa. Basically, when we start with parametric equations, we have two equations. So we have to figure out a way to turn that back into one equation that only has x's and y's. So the way we do that is we solve one equation for the parameter of t, then we plug that equation into the second equation, and then we should be able to solve and get an equation that no longer has the parameter t in it, and that's what we consider a rectangular equation. Sometimes we use identities to help us eliminate the parameter when we're dealing with trig functions, so we're going to fall back on our trig identities: sine squared theta plus cosine squared theta equals 1, or possibly 1 plus tan squared theta equals secant squared theta. So those are the different ones that we'll be using. Okay, so the first one is kind of an introduction, just to give you a little bit idea of how this works, and then we're going to skip question 1 for today, and that's going to be our warm-up for Parametrics Day 2. It's a little more involved than I would like to start out with. I'd like to give you a chance to kind of get your understanding down before we tackle one that's a little more complicated. So this is the introduction problem in your notes. X equals t squared minus 4, y equals 1/2 t, and then it gives us a time window of -2 to 3. So notice that you have your t value here and you have your t value there, and this right here, that's your time. Now, sometimes it will give it to you and be nice like this one. Other times you're going to have to figure that out for yourself. So you have to just be kind of careful about that. So what we're going to do is sketch the curve, and we're going to show the orientation. So the first thing you're going to need is an orientation table for the problem. And an orientation table is a 3-column table. It starts with time values. If you know them, you use them. If you don't, you'll have to figure out what reasonable time values are. You're going to have an x column, which is representing that equation, and a y column that's represented by that equation. So right now in the beginning, we're going to kind of, since it gives us time -2 to 3, we're going to calculate several time values. But sometimes your orientation table can be as minimal as 3 points or have more. Okay, so the first thing we're going to do is list all our time values in the table that we're going to use, and then we're going to take our time and we're going to plug it into each equation. So if I take -2, I put -2 squared here. -2 squared gives me 4. 4 minus 4 gives me 0, and that would be the value that goes in my table. Then to get the next one, my t in my y equation, remember, still that t value is -2. So 1/2 times -2 is -1. And then we'll continue this process of completing the table. So when t is -1, I get -1 squared is 1. 1 minus 4 gives me -3. And then 1/2 times -1 gives me -1/2. So when time is 0, 0 squared is 0, minus 4 is -4, and 0 times 1/2 is 0. And when time is 1, 1 squared is 1, 1 minus 4 is 3, and then 1 times 1/2 is 1/2. And 2 squared is 4, 4 minus 4 is 0, and then 1/2 times 2 is 1. And then our last time of 3, 3 squared is 9, 9 minus 4 is 5, and 1/2 times 3 is 3/2. And remember, we'll just keep everything in fraction form. So now how we graph our curve then is graphing in order from time -2 to time 3. We graph these points. So our first point is at 0, -1, so that's that point right there at time 2. And then when time is -1, it's at 1, 2, 3, and it's down here at -1/2, so it's right in here. And then when time is -4, it's at 0. When time is at 1, it's at -3, +1/2. When time is 2, it's at 0, +1. And then when time is 3, it's at 5, 1.5. Okay, so now we connect it in order of the time. So that means I'm coming this way, and I'm slingshotting around this way, I'm going out here, and then I stop. There is no arrow to that graph at the end. It doesn't go past that point, but the orientation, remember, says we start at this point and work our way around here. So we start here and we work our way around there. So that means you're going to put arrows on your graph to show orientation. And so that would be my final graph. Okay, so on the introduction video, I asked you to practice using the calculator. So we're going to actually look at this problem on the calculator. So the first thing we're going to do is put the calculator in parametric mode. So I press the mode button, I go down to where it says function, arrow over to parametric, hit enter. So that takes care of that. Then I'm going to go to my window, and it tells me my time is -2, 2, 3, and then t-step of, well, let's say, I'm just going to pull these off here as I went through this. Let's do a t-step of 0.1. That's kind of the standard right there. And then we're going to set our window. So we're going to go from what to what on our axis. What would be a good window? So keep everybody, if you're practicing at home, to keep everybody kind of in the same window to get this graph, I'm going to go from -5 to 5 and 1, and -5 to 5 and 1, and that'll just kind of give me a basic graph here. So then when I hit graph, it would help if I actually put the equation in there. Sorry about that, guys. Let's go into y equals and put in our equations. That's kind of an important thing to forget. Sorry about that. So when I press the xt theta, this time I get t's instead of x's, and I'm going to square it, and I'm going to put -4. And remember, that was our x equation. And then we're going to go into our y equation, and we're going to put 1/2. So we can do 0.5, and we're going to press xt theta again, and we get t. So we have two equations to represent this curve. Now let's see if we get the curve that we just drew. Okay, you can see that? All right, now here's what I want you to do. Go to y equals, arrow back behind the xt theta, and we're going to hit enter and change our line to, I want the 0 with the tail right there. So what that is going to draw a line and leave a trail. So you can see, there we go. Well, let's see one more time, third time's the charm. So open circle, hit enter, and then graph. There we go. So you can see that little dot on it, and there is our time. All right, so window changes, equations change, we're good to go. All right, so that was the introduction. So just kind of reviewing what all the stuff is and how. So this is kind of how we're going to do the. Okay, so we're going to skip that first example, and then we're going to move on to, I think I said that on the last one, but just want to make sure we're not forgetting about example 1. We're just going to do that in the next lesson. So now we're moving on to problem 2, and you can see problem 2 is a trig-oriented problem. And so when we do this, it's not going to be getting rid of the parameter of t. We're going to have to use a trig identity to do that. So what we're being asked to do, eliminate the parameter, create an orientation table, sketch the graph, show the orientation, and then again we're going to double check to see what we know about those rectangular equations from Algebra 2 and make sure everything kind of matches up. So in this case on the note page it doesn't give you a time window, but we know whenever we're dealing with cosine and sine that oftentimes we go from 0 to 2 pi, so that's what I'm going to use as my time in the table. Does that make sense to the problem? Okay, so to eliminate the parameter in this case, because there's not a t there, we're going to use an identity to do that. So we're going to use sine squared theta plus cosine squared theta equals 1. So that's the identity that we are using. Okay, so what we're going to do then is we're going to use our x equation and our y equation, and we're going to manipulate it to fit in this identity. So first I'm going to take x equals 3 cosine theta, and I know in my identities I need cosines and sines, so I'm going to solve this, manipulate this equation, and get cosine by itself. So that means I'm going to have x divided by 3 equals cosine theta. That's real close, but what is the identity? It's not cosine theta, it's cosine squared theta. So in this instance now, to make it match and go into my identity, I need to square both sides. And so when I do it, x times x is x squared, and 3 times 3 is 9, and that's what cosine squared theta is going to equal to. So now we're going to do that again with our y equation. Isolate sine, so I'm going to get y divided by 4 equals sine theta, and then I'm going to square both sides so I can use my identity, and then I have y times y, which is y squared, over 4 times 4, which is 16, and that equals sine theta, sine squared theta. So now I can make a substitution into my identity and get rid of all of the extra parameters in the problem. So this is sine squared, so I'm going to put y squared over 16 plus cosine squared, which is x squared over 9, and that equals 1. So hopefully that equation looks a little familiar because it's an equation we studied last time. It's a conic section, right? Two fractions connected by a plus sign set equal to 1. So what kind of conic section is it when we have two fractions connected by a plus sign? It's an ellipse. And last time we learned how to tell if it was going to be vertical or horizontal. So since 16 is the bigger denominator, right above it is the y. Y's run vertically, so this is a vertical ellipse, which means the major axis is running vertically and will be longer than the minor axis, which is running horizontally. We also know from the equation, because there's no plus or minus with either the x or the y, that the center of my ellipse is at 0, 0. So when I get to the point where I'm graphing after I create my problems in my orientation table, I want to keep that in mind. I should end up with an ellipse that's longer vertically than it is horizontally, and its center is going to be at 0. So it's always important to stop and take a look at what you know about the rectangular equation that you just got, because that's what this is. That is the rectangular equation. Okay? So now we're going to go to our orientation table. And I told you that I was going to use my values from 0 to 2 pi. So now I'm going to work through my table. So I'm going to go ahead and calculate each step out, but I know some of this you can probably do in your head, and you would probably do in your head and just write the answer down in the table, and that's fine. So we're going to do 3, and then I want to know what cosine of 0 is. So cosine of 0 is 0, and 3 times, sorry, that's not true. So cosine would be 1, and then 3 times 1 is 3. Okay, so now I write my 3 down, but this time it's cosine of pi over 2. So cosine of pi over 2, that's up on the, straight up on your unit circle. So the cosine value would be 0, because you're just moving straight up, and so 3 times 0 is 0. And then we're going to say 3, and we're going to say cosine of pi. So cosine of pi is going to be -1,
and 3 times negative 1 is negative 3. And then we're going to have 3 times, and the cosine of 3 pi over 2, so the cosine of 3 pi over 2 would be 0, and I get 3 times 0 is 0. And then finally, 3, and then I would say cosine of 2 pi, so cosine of 2 pi would be 1, and 3 times 1 is 3. So then for the y equation, we're going to have 4 times sine of 0, which is going to be 0, so that equals 0. Then you're going to have 4 times sine of pi over 2. Sine of pi over 2 is 1, so that's 4. Then you're going to have 4 times sine of pi. Sine of pi is 0, so that gives you 0. And then we're going to have 4 times sine of 3 pi over 2, which is negative 1. 4 times negative 1 is negative 4. And then we have 4 times sine of pi over 2, which is once again 0, which makes that 0. So we plot those points. So we have 3, 0. We have 0, 4. We have negative 3, 0. And we have 0, 2, 3, 4, and then we would be right back here where we started. So what is this going to look like? Should be a little bit longer in that direction than the other. So now if you think you're finished with the graph, then you missed the most important thing. What did we say that parametric equations had to have? They had to have orientation marks. So when you're graphing this, you can't stop there. You've got to actually show the direction that it was graphed. So we began with this point, then we went to this point, and around like that. And that shows the motion on the graph. So now we are finished. So we're going to practice one more time with this one on the calculator, and then we're probably not going to do the calculator on the rest of them. But just so you can make sure that on your calculator you can get this graph. Okay, so first thing we're going to do, so I don't forget this time, is we're going to go into our x1t, and we're going to put 3 cosine time, right? And then we're going to do 4 sine time. And so we have our two equations. And then we're going to go to the window, and we said we were doing 0 to 2 pi, so I'm going to do 0, and I'm going to do 2 pi, and then I'm going to count by pi over 2s like we normally do. So second pi divided by 2, and then we went 3 and 4 in each direction, so 5 to 5 should be fine, and we're going to graph. Well, that's kind of hard for you to see. I'm going to zoom in here a little bit. You can see that a little bit better. All right, so that doesn't look anything like my graph. That's a diamond. I need an oval. So what's happening here? What did I put in my calculator that caused this to happen? Well, remember we talked in the introductory PowerPoint about that t-step? And if we did our t-step in pi over 2s, which we're accustomed to counting to, that means I'm only putting a point every 90 degrees. And that's pretty far apart, so we don't get that nice pretty curve because those t-step points are far apart. So I'm going to go back down here and put it to 0.1 like we did in that first graph that we did. And when I hit graph, you can see how that graph looks a lot different. However, that looks more like a circle instead of an ellipse. So we're still not quite there. One of the things that you can do to square this up, which means to graph it proportionally with the same number of pixels across your screen horizontally as vertically, is you can press zoom and we can square this thing up, which is number 5. And if I do that, I finally get a graph that actually looks like what it's supposed to look like. So those are a couple little tricks of things that you can do when you're working through problems to work with your calculator. All right, so hopefully you feel like you have a decent grasp on that. All right, moving on to problem 3. Let me zoom back out here a little bit. There we go. All right, so problem 3, we have x equals t plus 1, and we have y equals t over t plus 1. Time we don't know, so we're going to have to kind of come up with the time for our table. And then we're going to eliminate the parameter, create the orientation table, sketch the graph, show the orientation, and we're not going to worry about the calculator on this one. All right, so how I go about eliminating a parameter in this case is I'm going to take one of the two equations, whichever one looks the easiest to solve for t. So I'm going to use this one right here. So I'm going to say t equals x minus 1. I just got t by itself. So now that I do that, I'm going to take that t and I'm going to plug it into this second equation. So I get y equals, and for t, I'm going to have x minus 1 on top, and then for that t right there, I'm going to have another x minus 1, and then I'm going to have plus 1. So my equation is y equals x minus 1 over x, and that's my rectangular equation. All right, so we eliminated the parameter. So looking at this equation, what do we know? We know it's a rational function. We know from our study of rational functions that it has nothing that cancels because I can't cancel these x's, so there's no holes. I know that my horizontal asymptote is at y equals 1 because the degree on top is 1 and the degree on bottom is 1, so the asymptote is at their ratio, which would be 1 over 1. I know that nothing cancels, so there's no holes. I know that it has a vertical asymptote at x equals 0 because since nothing cancels, what's left on bottom is where the vertical asymptote is. And then we have an x-intercept at x equals 1 because on the top where the x is, what would x have to be to make the top become 0? So I know quite a bit about that. Does it cross the horizontal asymptote? Well, how do I know if it crosses the horizontal asymptote? I take my simplified equation, which in this case is x minus 1 over x, and I set it equal to the horizontal asymptote, which in this case is 1, so I'll do it as a fraction, 1 over 1. And so what that leaves me with is 1 times that equal to x times that. And I know that when I have the same variable on both sides, that's going to cancel. And that means I'm left with negative 1 equals 0. Can that be true? Absolutely not. So we know that no, it does not cross the horizontal asymptote. So that should give us a really good idea of what this graph looks like, even if we didn't have an orientation table to worry about. Okay, so down to the orientation table we go. It didn't tell us what time, so we really need to kind of be able to come up with some things that might be reasonable. So we need some negative, we need 0, we need a positive. So I'm going to do -3, -2, 0, and 1. Because even though I have two branches, I do have to show on a rational function, I need to show the orientation on both branches. So I'm going to plug -3 in. -3 plus 1 is -2. -2 plus 1 is -1. 0 plus 1 is 1. 1 plus 1 is 2. So just plugging in for that t. So over here we're going to plug in the t on top and the t on bottom. So -3 on top, -3 plus 1 on bottom. So I get the fraction 3/2. And then I have -2 on top, -2 plus 1 on bottom. So that's going to give me 2. And then I have 0 on top, 1 on bottom, so I know that's 0, and then I have 1 on top. 1 plus 1 is 2, so 1/2 on bottom. So minimum I can have on an orientation table should be 3 values. I'm going to have a few extra ones here just because I know it's rational with some extra stuff there. Alright, so then as I graph this, I know that I have the point 1, 0. So point 1, 0 is right there. I know that I have a -2, and then I have 1.5. So it's there. I have, the -1, +2. I think I got off a little bit. -2, 1.5 should be right down there. And sorry about that. And then I'm going to have -1, +2, so that should be going up a little bit. Then I have 1, 0, and then I have 2, and I have 1/2. So basically, I have this going on, and the orientation then is going to go this way, and then it's going to hop over and continue this way. So does this graph match what we knew about our rational function? Yep, we can see that it has the horizontal asymptote is happening right in here. If my drawing was a little better, and the vertical is happening there. It did have an x-intercept here, no holes, so it kind of matches up. All right. Problem 4. So problem 4, again, we're going to eliminate the parameter. We're going to create the orientation table, sketch the graph. Again, on this problem, there is no time given, so we have the leeway to play with time, and minimum of 3 values there. So how are we going to do our rectangular equation? We're going to use our identity. So we're going to use sine squared theta plus cosine squared theta equals 1. You should write your identity down when you decide you're going to use it in the problem. So I have x equals 4 sine 2 theta, and so I need to get sine 2 theta by itself. So I have x over 4 equals sine 2 theta, and then I'm going to square both sides. So I have x times x, which is x squared, 4 times 4, which is 16, and that equals sine squared 2 theta. Now remember that this is just a horizontal compression by 1/2. It's not really changing the values, so technically our identity that we're using is sine squared 2 theta plus cosine squared 2 theta equals 1. Alright, so then our other equation is y equals 2 cosine 2 theta. So I'm going to have y over 2 equals cosine 2 theta. Then I'm going to square both sides, and I get y times y, which is y squared, over 2 times 2, which is 4, and that equals cosine 2 theta. Alright, so then I'm going to actually go to my identity, and I'm going to have sine squared theta, so I'm going to have x squared over 16 plus y squared over 4, and that equals 1. So now I have my rectangular equation. So what do we know about the rectangular equation? We know it's an ellipse. We know because 16 is the biggest one and it's below the x squared that it's going to be a horizontal one, so it's bigger horizontally than vertically. There's no plus or minuses with the x squareds, so that means my center is at 0, 0. Alright, so now moving on to our orientation table. So before, remember I said that you only had to have a minimum of 3. Well, I know that I'm using time values. I know that I'm going to go at least 0, pi over 2, and pi. So those would be my first 3 values. And what I'm going to do is use those to see if that's enough to confirm my orientation. Okay? So on this one, I would do 4 times, and then I'm going to do sine of 0. So that's going to be 0, so that equals 0. And then I'm going to do 4 times sine of pi over 2, which is 1, which is going to give me 4. Then I'm going to do 4 times sine of pi, which is 0, and that's going to give me 0. All right, then I'm going to come over here to my y equation, and I'm going to do 2 times cosine of 0, which is 1, which is 2, and 2 times cosine of pi over 2, which is 0, and that's 0. And then I'm going to do 2 times cosine of pi, which is -1, which is going to be -2. And I think that's going to be enough to be able to show me my orientation. So I'm going to go over here to my graph, and I'm going to plot those points. So I have 0, 2, so I'm right here. And then I have 4, 1, 2, 3, 4, 0. And then I have 0, -2, and because I know this is a symmetrical shape, I now know I have -4, 1, 2, 3, 4, 0. So there's where my ellipse is going to be. Okay, so there's my orientation. So which point did I begin with? I began at 0, 2, but this time I went to 4, 0. So my motion on this particular problem is moving this way. All right, so last one, number 5. So we have x equals t cubed, y equals 3 natural log of t. So we might actually need our calculator here to calculate table values. So I have to watch out for that because it doesn't give me time. Okay, so to eliminate the parameter, this isn't a identity one because it's not cosine and sine. It's x's and y's and t's, so that means I look at the equation that I think is going to be the easiest. So I'm going to use this equation to get t by itself and then plug it into that. So x equals t cubed. And so how do I get t by itself? I take the cubed root. So t is going to be the cubed root of x. And then what do I do with that equation? I plug it into the second equation. So then I have y equals 3 natural log, and I'm going to write this as an exponential form. So I'm going to do x to the 1/3 because I know that my log rules have a power rule in it, so I'm going to go ahead and use it as a power. So now what do we know about the 3 that's in front of the log according to our log rules? It needs to be bumped back up to where it belongs, which was right there. And then I know that anytime I raise a power to a power, I can multiply. So 1/3 times 3 is just 1, which gives me y equals natural log of x. And that's my rectangular equation. Okay, so dig back and let's think about what we know about this one from Algebra 2. Y equals natural log of x. Well, we know it's the natural log. We know that it has a vertical asymptote at x equals 0. We know that this is a base E, and base E is approximately 2.718, in case you forgot. We know that the domain is from 0 to infinity, and we know that it has an x-intercept at 1, 0 because it is that parent function. So that should give us a pretty good idea of what this is going to look like. The orientation table gives us the direction of motion, and that direction of motion should still be mirrored what you know about that graph. All right, so in my table, I'm just going to kind of keep it simple, and I'm going to use 1, 2, and 3. And I'm going to use my calculator to kind of help me do some of the calculations that I don't know. So 1, 2, and 3 are small numbers because I'm going to have to cube, so I really don't want to have to make them huge. Remember, this is to get our orientation. So I'm going to do 1 cubed, which is 1, 2 cubed, which is 8, 3 cubed, which is 27. Then I'm going to move over here. So remember, I'm doing 3 times the natural log of 1. So 3 times the natural log of 1. So in our home screen, if you need to kind of check this, you could do natural log of 1, but hopefully you know and remember that that's 0. So technically this is 0 times 3, which is 0. That's one we worked with in Algebra 2. So now we can do 3 natural log of 2 and 3 natural log of 3. So I've got some decimals to put in there. So this is 3 natural log of 2, which is approximately 2.079, and 3 natural log of 3, which is approximately 3.296. And so when I look at those numbers, I should be able to kind of get my orientation. I know that it's natural log. I know that we have this asymptote that's running along here. I know that it graphs at this point 1, and I know that this graph is going to look like that. And the orientation is moving that way, and I know that from the table. So be careful that you're putting your orientation here and you're not just extending the graph on forever. Now we don't have a specific set of time on this, and we picked the time for the orientation, so technically the nature of this graph does go on, and so that's why I felt comfortable putting the arrow at the very end, but really the arrows are here for my orientation. So that takes care of the problems for today. You have some textbook problems to practice, and then we will do more parametric equations next class or next lesson. Thanks so much. Bye guys.